In this video, we're going to take a look at our communications EMI, and to do that, we're going to consider two systems I've drawn here below. Each of these systems is going to be transmitting data at a certain frequency. On the left, we'll have frequency F1, and on the right, frequency F2. And so if we take a closer look at these systems, so starting on the left, we have system 1, which has a transmitter T1, and it's transmitting some signal over free space to a receiver R1. And so we can see from the waveforms down below that our transmitter has a carrier frequency of F1 and our receiver has a band pass centered on F1. So basically whatever is sent at F1 is going to be received at R1 and everything outside of this pass band is going to be blocked. Similar thing in our system 2 on the right. We have transmitter T2, which is transmitting some signal through free space to our receiver R2. The only difference is now that our carrier frequency is F2 and our bandpass filter at our receiver is centered on F2. And so what we can say, comparing these two systems, is so long as our F1 and our F2 are different, we shouldn't be having interference. So F1 not equal to F2 is going to result in no interference. And so of course, in practice, if they're close enough, we might still see some interference depending on the quality of our band pass filters and exactly how close F1 and F2 are. But in this case, we're saying that our receiver R1 is only receiving signals from T1. So only signals from T1, and then same thing with our R2. So our R2 is only receiving signals from our R2 is only receiving signals from our T2. So something like this. But on the other hand, if we say that the two frequencies are equal, then we are going to have some interference. So for F1 equals F2, we're going to have interference. And so the reason we're going to have this interference is because our receiver R1, for instance, can't distinguish between a signal from T1 or T2. So cannot distinguish between a signal from T1 and T2. And so of course the same is true of our receiver R2, so it's not going to be able to distinguish between signals coming from T1 and T2. And so when we have this situation, it's actually a specific type of interference called co-channel interference. And so other than having different frequencies, and remember the frequencies don't necessarily need to be exactly the same, but for instance, maybe if we had our F2 somewhere such that it was inside this bandpass filter, that would still cause some co-channel interference. But other than having these frequencies separated, what is another way that we could make sure that we don't have this co-channel interference issue? So if we think about that for a second, so let's just say, assume our F1 and F2 are the same. How can we avoid co-channel interference? And so the answer is, of course, to appropriately separate these two systems over geographic space. So let's say appropriate geographic separation. And so the reason for that is, of course, we touched on this a little bit when we were talking about high frequency signals, but there's going to be some limited amount of power in our signal at our transmitter. Of course, we're losing power as we travel through free space. So if this power or necessarily we could do this for all powers, but for a given power, we would have some limit as to how far it could travel. So if, for instance, our signal from our T1 can only travel 1 kilometer, let's say. Of course, we want our R1 to be within 1 kilometer of T1, but if the distance from T1 to our R2 is, let's just say, 100 kilometers, then of course we wouldn't have to worry about R2 picking up any signals from T1. And so of course there's various things to consider. In addition to the power of our transmitter, we have things to consider such as our antenna direction, our antenna gain, again, items that we kind of briefly touched on in talking about our high frequency circuits. So one other type of interference we can have in our communication EMI is when our two frequencies F1 and F2 combine in a nonlinear circuit. So F1 and F2 can combine in a nonlinear circuit, and so normally this is occurring in our transmitters or our receivers. So transmitters and receivers. It is possible for this to happen in passive elements if we have really high power transmitters, but that's pretty uncommon. So typically this is going to be happening in our active transmitters and active parts of our receivers. So by combining in a nonlinear fashion, what we're ultimately going to have is we're going to have new frequencies that are harmonics of that combination. So we'll have multiples of the sum and multiples of the difference. So we'll have multiples of F1 plus F2 and multiples of F1 minus F2. So we have these harmonic frequencies. And so we saw that a little bit with our RF mixers. And so the type of interference that can result from this is called intermodulation. And so one example of how this type of interference could come about is, let's say we have some system up here. So let me copy this just for clarity. So let's try that again. Okay, good enough. Let's bring that down here. So let's say we have some new system that has carrier frequency F3. So now we have T3 and R3 and a carrier frequency F3 and a bandpass filter centered on F3 as well. Well, what if we have in some other transmitter, we have over here our maybe we have our T1 transmitter from before, and in that transmitter, for some reason, we have these two frequencies, F1 plus F2, that are interacting, and they create this harmonic distortion such that this is equal to F3. Well, of course, this receiver R3 would not be able to distinguish between this harmonic product of our nonlinear circuit compared to the signal that is being sent from transmitter T3. So that would be an example of how we could have intermodulation.